Welcome back for part 3 of the derivatives of inverse trig functions, this time the inverse of tan. Now once again we'll start by having a quick look at GeoGebra. The green lines here are the tan of x, the tan function. Remember tan is a cycle that repeats every pi, so at negative pi over 2 tan tends to negative infinity, and at pi over 2 tan tends to positive infinity. So as you can see, where point A is here, that's nice. As point A comes along the tan function, point B follows along the mirror or the inverse function, the mirror image there. And I want to be careful I don't go too far here, otherwise point A will suddenly cross beyond and onto this next part here of the function. Now that doesn't have an equivalent reflection, this part of the tan function. If it did have a reflection, it would be further down here, and then we would again be breaking the rule for definition of a function. The red graph would fail the vertical line test if there was another copy of this further down. So therefore we will have to limit the domain of the tan function, the original f of x, the green one, to be negative pi over 2 to positive pi over 2. That way we'll have a well-defined inverse. I almost lost point A then. If I go too far up there, point A, I'll jump across onto this next one. It'll reappear down there somewhere. So point B, of course, could continue along there forever if I was game to push point A further up without losing control of it. If I zoom back, you'll see what I'm talking about. So point A could continue. Oh, I lost it. Point A went too far. It's just such a small forwards increment in x, so point B would therefore sort of continue out along there. But we wouldn't be wanting to have extra copies of this red graph above and below. That would break the function rule. So let's zoom back in again to something approaching normality, and as long as point A behaves itself and just stays from negative pi over 2 to positive pi over 2, then everything will be just fine. So that's the limited domain there. Now, let's go about finding the derivative of this function. So, as always, we will begin by taking the tan of y, and that would equal x. Like always, we're trying to find dy dx of this original function. Now I will use implicit differentiation, which we've seen a couple of times now. So dy dx d over dy of tan y equals the derivative with respect to x of x. So dy dx, now derivative of tan, if you don't remember, you can check one of my videos on the previous videos about this. The derivative of tan is sec squared y, and the derivative of x, of course, is 1. So let's just take a bit more of a look at what we've got to deal with here. Dy dx, yes, would be 1 over sec squared y. Now the Pythagorean Theorem, remember it's cos squared y plus sine squared y equals 1, but that's not much use to me because I have sec squared. So remember sec was 1 divided by cosine. So what if I divide everything by cos squared y? Oh, that's 1. That's tan squared y, and that's sec squared y. So I could use 1 plus tan squared y here. Dy dx is 1 over 1 plus tan squared y. Now what was tan of y? If we scroll back to the top there, tan of y was the same as x. So this is really 1 over 1 plus x squared. That is my derivative, dy dx, when my original function started as y equaled the inverse tan of that completes the 3 videos in this little series about the derivatives of inverse tan functions. Now, of course, any of these new rules could be combined with other derivative rules, like chain rules, or product rules, or quotient rules, or any combination of the above, just to make life interesting. All right, see you next time. And don't forget, if you have any questions about these, you're always welcome to drop me a line in Teams or by email.